Okay, so we previously calculated probabilities for standard normal, right? Okay, so standard normal is a normal distribution where your mean is equal to 0 and the standard deviation is equal to 1, right? Okay, so why we started with the standard normal case is because why we started with the standard normal case. So standard normal, Z is normally distributed with mean 0 and standard deviation 1, is because we use tables, right? And those tables are only given in the standard normal case, right? Okay, so now what we want to do is we want to calculate probabilities, right? Like what we did calculated for standard normal, but now what we want to do is we want to calculate it for a normal distribution that is not necessarily standard, right? Okay, so a normal distribution where the mu can be anything and the standard deviation, the sigma, can also be anything, right? Okay, so how we do that is essentially by using a substitution, right? So typically what we're given is we're given, say, a problem like this over here. And essentially what you're going to do is you're going to use a substitution to convert this over here into Z, right? Okay, so you're going to convert what is the random variable that you're interested in, the normal random variable that you're interested in is X, right? And you're going to use a substitution over here, right, to convert it to standard normal Z, right? And then once you convert it to standard normal, then you use the methods that we had from before, right? So the methods that we had from before is these sort of problems over here that I discussed in the last video, right? Okay, right. So this is basically how you this is going to tell us how the substitution is going to work, right? Okay, so x is normally distributed with any possible mean and any variance over here, right? So x is normally distributed over here. So x is normally distributed with any mean mu, any standard deviation sigma. Okay. And how we're going to do the conversion, do the substitution is using this result over here, right? This proposition. Alright, okay, so using the substitution over here, right, z is equal, so x is what you're working with and you're converting to z over here, right? Okay, so essentially the results are over here, stated over here and over here, right? Okay, so if I have a normal distribution, big X, right? Normal distribution that any mean mu, any standard deviation sigma, and I want to get probability that it lies between A and B, right? You want to notice the structure over here. You want probability between A and B. That's similar to what we did before, where we had a probability Z between two values over here, right? Anyway, so in this case, this is X, right? Okay, and what your substitution is going to do for you, it will convert this X, big X over here, into Z, right? And the values over here, the A will convert according to your substitution, right? So this small x, this value of x over here, which is A, right, will feed into this formula. So you put the A into here, and you get A minus mu on sigma, which is this. Okay, and likewise the B over here is going to convert, right, to a Z value, and the conversion to a Z value is again by this substitution here. So it's B, this B over here is going to convert to B minus mu on sigma, which is this, right? Okay, so to get, if you have X, a big X, that is a normal distribution, the general case, where mu can be anything and sigma could be anything. We want to get a probability of that normal x line between A and B, and you're calculating using tables, right? This is how you're going to do it, right? You convert the A using a substitution, and you convert the B using a substitution, right? Okay. Uh, Now this is for a two-sided interval over here. If you have a one-sided, it's the same idea, right? What's going to happen is the substitution is going to convert the big X, if you want, to Z over here. And the key thing over here is this B value is this B value over here. So this endpoint of your interval, right, is going to also convert, right? See, like exactly like how this B over here converted to B minus mu on sigma. The B over here converted to B minus mu on sigma. Right? Okay. Right. So probability X is less than B. So for this one-sided interval over here, right? It's same idea as over here, right? And similarly, probability X bigger than B, you're just going to use the same sort of form over here. So if you have X bigger than B, all you're going to do over here is just change this to bigger than over here, right? All right. Okay. So where does this actually come from, right? It comes from using a substitution and an integral, right? So if it, let's just probably go through this very quickly, right? All right. Okay, so let's see if we could justify this proof, right? Or explain this proof. Okay, so I want to explain this statement over here, right? This proof actually deals with both cases, but let's just look at this one to give you an idea, right? Okay, so what I want is probability A X line between A and B, right? So probability of the big X line between A and B, right? What you want to do is you want to use the PDF of the big X, right? Now X is normally distributed, so it has a PDF of this form. We talked about this in the last video, right? So the PDF is exponential times this factor, right? And if you want to get a probability for a continuous random variable, what you need to do is you need to integrate between your limits over here, A and B, right? So integrating between A and B, right? Okay, so far all you're doing basically is you're just using your definition of probability for a continuous random variable to go from here to here, right? Okay, and now what you do is you use this substitution here, z is equal to x minus mu, right? And when you do that, right, well, you want to think that you're using small z is equal to small x minus mu on sigma. When you use that substitution, when you're doing any substitution, remember, and it's a substitution for a definite integral, your limits are going to change over here, right? So the b over here, according to this substitution, will become b minus mu on sigma, which gives you this. And the a also will convert to a minus mu on sigma over here, right? And the x minus mu on sigma squared, right, will convert to z squared. The 2 will come along. This sigma is gone from differentiating the substitution and putting it in. And so you get this, right? Now, if you look at this over here, right, this exponential with the minus z squared and the 1 on root 2 pi, right? This over here, this is a PDF for standard normal, right? Okay, so what you're doing over here is you for a PDF for standard normal, you're integrating between these two values, and integrating between these two values for the PDF of a standard normal is actually calculating this probability, right? So that's how you actually go from this side over here to this side over here, right? Really, you working out this integral and you're using a substitution that looks like this, right? You want to think that W is just let that W be small z, right? You could use a W, in which case it's a dummy variable, and then you'd have to flip it back, but no real need, just use small z over here is equal to x minus mu on sigma. Anyway, so that's really to give you an idea of how that proof works. Okay, so let's see an example of using this result over here, right? This order substitution. Okay, so I'm given this x over here, which is normally distributed, right? It's normally distributed with mean 50 and standard deviation 10, right? So x is normally distributed with mean 50 and standard deviation 10 here, right? Okay, and what we want to get is we want to get probability that the big X lies between 45 and 62, right? Right. Okay, so what you do in here, in order to work this out, you're using this result over here, right? So first thing you're going, well, using this result over here is going to convert the problem involving the big X into a problem involving Z, right? Okay, so this is your problem over here, the big X. We want a probability that lies between 45 and 62, right? Okay, so you're using your substitution, right? And the substitution is you take your value over here, you subtract the mean, and you divide by standard deviation, right? You take your value over here, right? Subtract by the mean and divide by standard deviation. Okay, so that is converting x values over here, this x value to a z value, this x value over here to a z value, right? And then the x will switch to z here, right? Okay, right, so you converted your problem over here into a problem involving z, right? And the thing is, we did problems just like this, right? So for example, this one over here, right? This is calculating probability for z line between these values, right? Okay, so the idea over here is that you start off with the x, which is a general normal distribution, right? And then you use a substitution to get something in just z, right? Okay, and notice the structure over here. Here you have two-sided interval over here. And likewise over here you end up with a two-sided interval, right? Right. Okay, so going from here to here, right, drew this diagram to show you what's happening, right? Okay, so the x over here, the big X, has mean 50 and standard deviation 10, right? So you're seeing the mean 50 over here, which is the center of your normal distribution. Notice it's symmetric about this 50 here. Right? Okay, and what you want is probability between 45 and 62, right? Okay, so for this normal distribution over here, right, with the PDF given by this green bell-shaped line over here, what I want is probability between 45 and 62, which is the shaded area over here, right? Okay, it is helpful sometimes to draw diagrams. In this particular case, this is relatively simple, and you probably don't need to draw a diagram to go from here to here, right? Because really you're just using this formula here, right? Anyway, but I drew this diagram to give you an idea of what's going on, right? Okay, so what you do now is you, as I said, you use a substitution. Z is equal to x minus mu on sigma. The mu is 50, the sigma is 10. And once you use that substitution, the 45 will convert to minus 0.5. The 62 will convert to 1.2, right? And this 50 over here will convert to 0, right? Which you expect, right? Because if you put 50 in over here, you get 50 minus 50, which is 0, right? And 0 divided by 10 is 0, right? Okay, so these three values over here convert respectively to these three values over here, right? And part of this conversion is that this area over here is actually exactly this area over here, right? The diagram isn't totally fantastic because what could happen is when you do the substitution, this PDF over here, this sigma is 10, right? And this sigma over here is 1, right? So really, for a more accurate diagram, this would have been have a more wide dispersion over here, right? And then this would be narrower, right? But however, this area over here would be equal to the corresponding area over here. Anyway, right. But really, this is just to give you an idea of the substitution, right? As I said, the diagram could be a little better. Right? Okay, so we have this over here. And now what we want to do is we want to get this probability, right? And that's getting so this probability over here, right? Okay, right. So how do we do this? All right, so we want to get the probability of the big Z line between minus zero point 0.5 and 1.2. All right, so I'm gonna explain this using this diagram over here, right? All right. Okay, so probability of Z less than 1.2 is this area coming back from the 1.2, which includes the red area and the blue area, right? So probability Z less than 1.2 is red area plus blue area. Okay. Probability Z less than minus zero point 0.5 is coming back from here to here, so it's the blue area. Now, what I want is probability between minus zero point 0.5 and 1.2, so I want the red area, right? Now, this red area over here, you could regard as, well, it's the red area and the blue area. So if you had the red area and the blue area, and you subtract off the blue area. Okay, but what's the red area and the blue area? The red area and the blue area is probability Z less than 1.2. The blue area is probability Z less than minus zero point 0.5. So I can get my red area being equal to this probability minus this probability, right? Okay. Right. Okay, so once I achieve that, right, what I'm doing is my two-sided interval like this over here, I express in terms of two one-sided, right? And now that you have two one-sided over here, what you're going to do is you're just using your methods from before, right? Right. Okay, so something that is Z, okay, so really you can use this result. If you could take a look at the previous video for an explanation of this and the diagrams. But for the Z less than 1.2, right, once it's less than, this is what the formula that you want to use, right? So Z less than 1.2, and this is the case of positive Z, so you're going to express this as the Z less than 1.2 is 1 minus probability Z bigger than 1.2. So that's how I get this guy over here, right? Okay, and then the probability of the big Z less than minus zero point 0.5, right? Again, I can use this formula over here, right? Now this small z over here is negative, right? Okay, so if I want probability of the big Z being less than something that's negative, that is equal to probability of the big Z being bigger than, you just take the negative of this, and if it's negative already, the negative negative would make this positive here, right? So that's how you go from negative over here to positive, right? So now that you have these over here, this is, now you're just going to use your table. You use your table and you want probability Z bigger than 1.2. So you go into your table over here, you come down, you have 1.2, and there's no need to fine tune with these, right? This is just 1.20, right? So 1.2 is this one over here. Right? Okay, and then the Z bigger than minus point, probability of the Z bigger than 0.5 is using this over here. So using the table, and you have your 0.5. Again, you don't need to use these over here because the decimal places over here, you're just up to one decimal place, right? So the probability of big Z bigger than 0.5 is you're using your 0.5 over here, and you used this one, so it is 0.3085. Okay, so you get this, this, and this, then you work it out and you get your answer over here. Alright, okay, so far what we were doing, at least in these problems, we're calculating probabilities, right? So we just over here calculated a probability, and then eventually, well, with this two-sided over here, we broke it down into two one-sided over here, and then each of these one-sided came directly from the table, right? Well, sorry, They did not come directly from the table. You actually needed to convert this one over here into something where it's z greater than, right? And likewise over here, you did the same thing. And then these over here, right? These two came directly from the table. Right, so if we're looking at, say, this one over here, just this probability z bigger than 1.2, right? Right, this over here, the answer for this comes from the table. Okay, so now what we want to do is we want to consider the reverse situation, right? Okay, so the reverse situation, an example, is given in this problem over here, right? So what you're given is you're told that you have a normal distribution, and you're told what the mean is, and you're told what the standard deviation is, right? Okay, and what you're trying to do is okay, so what the problem is asking you for is it's giving you this probability over here, and is asking you to figure out what the small x is, right? Okay, so over here, right, what you're given is basically you're given the value, you're given the z value, and you want to work out the probability. This is the reverse, right? You're given the probability over here, and you need to work out the value for the random variable, right? Okay, so this is a diagram. These diagrams over here will explain this answer, right? Okay, so I have that the big X is normally distributed with mean 40 and with standard deviation 6, right? Okay, if you're doing these problems now, in this case, it is advisable, highly advisable, that you draw a diagram to figure out what's going on over here, right? To see, right? Okay, right. So I have my normal distribution over here. The mean over here is 40. And what I'm trying to do is I'm trying to figure out what the x is over here, right? Now, when you're doing these problems, what you want to do is you want to get an idea of where this x is going to lie first of all, right? And that you can get by looking at this sort of probability statement here, right? Okay, so the main thing is really this small x over here. Well, is it going to be on this right hand side or is it going to be on this left hand side, right? Okay, right. Okay, so this is the statement over here with probability big X being equal to the small x, right? The probability over here is 0.14, right? And the key thing that you want to realize over here is this 0.14 is in fact less than a half, right? Okay, so it's the big X bigger than something, right? So if it's big X bigger than something, what you're looking at is an area to the right over here, right? Okay, so an area to the right, okay, a right tail over here, right? Now, there's no way that that small x could be on this side, right? Because if that small x was actually on this side over here, right, it would mean that the probability would actually be bigger than a half, right? Because if you're at 40, right, and you consider the area to the right of 40, the area to the right of 40 is in fact zero point 0.5, right, or half, which is your total area. Remember, this is a PDF, a continuous random variable. Your total area is 1. So total area is 1, which means that if you look at this divided line over here and you look at the area to the right, that area is a half, right? Okay, so what I'm saying is that small x could not be over here, right? Because that would give you, when you work out this over here, if that small x was right there, then you'd get 0.5, right? Which is not what you have. If the small x was over here, right, then the probability that you would get would be larger than 0.5, say like 0.6 or something like that, if the small x was over here, right? So the fact that this is less than 0.5, this probability is less than 0.5, means that this x over here needs to be on this side, right? Okay. And we'll see similarly for this question over here, we need to figure out this location of the small x, what side it's on, right? But we'll get to that, right? So first thing is based on the fact, looking at this over here. Okay, so you're looking at two things, right? You're looking at this direction, right? This is greater than, right? So greater than means you're looking for a right tail. And the fact that this over here is less than 0.5 means that you're going to be on this side, right? Okay. Now, once you have that, right, and you have this diagram, what you're trying to do, so you have the 40 over here and then you have the x over here. You don't know if it's going to be over here. Well, actually, you can get some idea because the 0.14 is this area over here, right? And there's no way probably that that small x is going to be like over there because then it would be larger, right? So the fact that it's 0.14 means that x is somewhere like around over here, right? Anyway, so if the small x is over here, so we know that the small x is here and that the mean is 40 and the small x is to the right of 40, right? Okay, and now what you're doing is, well, we want to work out what this small x is, right? And eventually what we need to do is we're going to need to use your table, right? So we need to use this table over here, right? And this table is in terms of z over here, right? Which means that in order to figure out what the small x is, you need to convert to z, right? Okay, so you're going to do a conversion to z over here, right? And in this case, it is helpful to draw the diagram, right? Now, when you do the conversion to Z, the diagram isn't going to radically change, right? You have a right tail over here, and likewise, you're going to have a right tail over here, right? Here, this is the original X with mean of 40. When you standardize, right, when you use the substitution, right, when you use the substitution to get you to Z, right, this mean over here will transform down to 0 over here, right? 40 minus 40 will give you 0, right? So this 40 comes over here, right? And then your x over here, which you don't know as yet, right, will also convert, right? It'll convert to some z over here, right? Okay, right? Now, so what you're doing is you have this statement over here, and you're converting it, right? You apply any substitution to this statement here, right? Okay, now when you apply any substitution to this statement, remember when you apply your substitutions, right? We talked about this a couple minutes ago. You apply a substitution. This area, in fact, does not change, right? The shape might change and so on, and the location obviously changes, but the area itself over here, corresponding areas. So this is for the big X, and this is for the big Z, right? This area over here is equal to that area over here, right? So when you do your conversion, right, the areas stay the same, and so your probabilities on the side stay the same. Right? Okay, so you're doing your conversion and you're applying your substitution over here to the big X and the small x. And that's doing it over here. So you do it over here and you're doing it over here. Now, doing this, applying this substitution over here to the big X converts it to the big Z here. And now what you have is that this over here, right, converts to this. Now this over here, what we do is we call it, for the time being, we call it small z. Right. Okay, so this problem over here converts to this, right, after your substitution. And what we're doing for the time being is we're calling this small z. Right. Okay, so that's how we get this line here. Right. And now what we need to do is we need to still figure out what the small z is, right? And figuring out what the small z is you're going to use the table, but you're not going to use it like how we did before when we came along the side over here and we fine tune over here. Now what you're going to do is you're going to actually come from this 0.14, right? You find the probability inside there, and then you actually find the z value corresponding to it. So you're going to find the probability over here and then come across over here and then fine tune up here, right? Okay, so that's where the name of the section comes from. Right, using the normal curve in reverse, right? Or if you want to use in the table in reverse, right? Okay, right. So what I want to do is I want to figure out what this small z is over here, right? And as I said, this probability, this 0.14, you look over here, right? Okay, so you look over here, and well, how do you find it? Well, you notice over here, it's zero point 0.5, and then as you come down this way, you actually decreasing, right? So you know that, well, you're gonna say, if you say start over here 0.4, right, and you're looking for 0.14, that means you need to come down, right? Okay, I notice you also decrease this way over here, right? So here this is 0.1469, and when you come this way it's a smaller value, and notice over here you get the 0.14, right? Okay, so when you doing these problems, sometimes now we okay, so what I have over here is 0.14, and what I have over here is 0.1401, right? If, for example, I had this was not 0.14, but this was 0.141, right? 0.141 would be, say, somewhere in the middle over here, in which case you'd need to use a sort of interpolation, right? And that's in the notes, but it's no longer part of the course, right? So what we the probabilities when you solve any problems, and so you should be, we'll set it up so that you should find probability would actually be one of these over here, right? Now with this 0.14, it's not exactly, I mean, it's 0.1401, but that's good enough, right? So we will work with this one. So we're just gonna say that the 0.1401 is practically 0.14, right? And we go from there, right? Okay, so once we have that, what we need to do is we need to figure out what this small z is, right? So we locate the 0.14, and we now just need to figure out what the small z is, right? So what's the small z? The small z is going to be 1, right? And then you come along over here, and then you add 0.08 to it, right? So this is one more time, right? So this is 0.14, my 0.14 over here, and this is 1.0, right? And then to the 1.0, I add a 0.08. So overall, I get 1.08, right? So I end up with my 1.08 over here, right? Okay, so that's using the table in reverse. I get that the small z is 1.08. And now what I need to do is I still need to figure out what the small x is over here. But that's not really a big deal, right? Because remember, the small z was actually just this x minus 40 on 6, right? Okay, so the small z was x minus 40 on 6. So the x minus 40 on 6 is the small z, which is 1.08. And this is easy to solve. Of the x, you carry the 6 across, carry the 40, 6 by 1.08, and then move the 40 across, you get this. So your small x turns out to be 46.48. So let me remind you about something we did in a previous video, right? So I want to calculate, this is not finding using a normal table in reverse, right? This is just the first way we did things, right? Okay, so we want probability the big Z is less than minus 1.25, right? So this here is, this green curve over here represents the PDF of your standard normal distribution, right? We want probability that the Z is less than minus 1.25, right? So I have my minus 1.25 over here, and probability Z less than minus 1.25 is equal to this area, this blue area here, right? Okay, so if I want to get this probability, right, you notice what's given in the table right tails, right? And this is a left tail, right? Okay, so in order to work this out, right, what you're doing is you're just going to convert this problem. If I want probability Z less than 1.25, right, you want to notice because standard normal is symmetric like this over here, I could consider this this blue area reflected across, and that would give me this red area over here, right? Now this red area over here, the area is equal to the blue area, right? So if I want to get this probability is equal to this area, and this area is equal to the area under the PDF, and the area under the PDF is the probability starting from 1.25 going onward, and this comes from the table, right? Okay, and the Z bigger than 1.25 is just going to come from the table 1.25 over here, which gives me the point 1056. Okay. Okay, so let's continue with these examples of using your normal curve in reverse, right? So now we're looking at this one over here, right? Now, as I said, when you're doing these problems, it's a good idea to draw a diagram, right? Okay, because you want to figure out where that small x is, right, relative to the mean, right? So what I mean by that is your mean for your big X over here. So big X is normally distributed with mean 40, right? Okay, and what you want to do is you want to get an idea if the X is on, small x is on this side or if the small x is on this side, right? And how you're doing that is look, you're going to be looking at the direction of this inequality and this probability over here. Essentially what you're going to be doing, you're going to look at it and see if it's less than 0.5 or bigger than 0.5, right? Okay, so in this case it's less than 0.5, right? Okay, and what I want is I want a probability that the big X is less than my small x, right? So I have my small x, and if I'm looking at this other probability less than the small x, I'm looking at a left-hand tail, right? So I'm looking at a left-hand tail over here, right? And your small x over here, it cannot be on the side, right? Because if it was across here, right, like over here, right, and you worked out this probability would be bigger than zero point 0.5, right? And that's not what we have, right? What we have is a probability that is 0.45, so it means that you're on this side, on the left-hand side of this mean, right? Okay, so the x is less than 40. The small x is less than 40. Right, so once we establish that, right, that the small x is less than 40 based on this probability over here and the direction of this inequality, we could draw a diagram, right? Okay, and now as before, what you do is you're going to use a substitution, right? So when you use a substitution, the 40 will convert to 0. This small x over here, right, with the substitution will convert to small x minus 40 on 6, right? And so the substitution that you're using, right, would be this substitution over here, right? Okay. Or, well, you've seen it here, sorry. Okay, so you're using the substitution over here. Okay, so this probability statement over here is going to convert to this probability statement over here. The areas do not change, right? So the areas do not change when you go from the x to the z, right? So that means that area over here is the probability, which is the 0.45, so that remains the same. And these over here, they change, right, according to substitution. Okay, so the big X is going to convert to standard normal under this. The big X is going to convert to standard normal, right? And the small x converts to this way. You put in the small x over here. And that we call small z as how we called it over here, small z, right? Okay, so now we have this situation over here where we have probability that the big Z less than the small z is 0.45, right? But now what's happening is that seeing that this over here is 0, right? And you're on the left hand side, that means that that small z is negative now. Okay, so what we want to get is we want to figure out what this small z is over here, the red z is over here, right? Okay, the z over here, small z over here is negative, right? Because your small x over here is less than 40, small x is less than 40. Then when you put it in over here, you get a negative value on top, right? When you divide by the 6, you're going to end up with something that's negative here, right? Okay, so your small z is negative, and what we would want to do is we want to figure out what the small z is after you use the substitutions and so on, right? The big X converts to big Z, right? And this small value, the small x over here converts to this, and we're calling that small z. Okay. Right, and what we want to do is we want to figure out what this small z is over here, right? But we can't use your table directly, right? Because your table is, well, for one thing, it's not for uh, right left tails like this over here. It's for right tails, right? Okay, and you're not seeing any negative values of z over here, right? Okay, so this to work this out, we need to use some symmetry, which is the example, the small example that we just talked about. Okay, so this small z over here, when I take the negative, okay, small z is negative. If I take the negative of it, I end up with minus z, but that minus z is positive, so I come across over here on my positive z axis. And also this red area over here is, will reflect. If I take the reflection of this, I will get the blue area, right? And those areas are identical from symmetry, right? So red area is equal to blue area, right? Okay, so now if you look at this situation over here, we consider this situation over here. Now this is our right tail, right? Okay, so your symmetry, the fact, okay, so big Z less than this, the red small z over here is 0.45, right? That's coming from the transformation, right? After using the reflections and so on, I get this statement over this picture over here in the blue, right? And this picture over here in the blue is saying that the big Z bigger than minus z, so I have a right tail over here. This area over here is the same 0.45, right? So this statement, it gives me this statement over here. Now once I have this statement over here, right, this is now a right tail, right? So this one over here is corresponding to a right tail. And if I have a right tail, what that means is I can use my table now, right? Okay, so right tail over here, right tail over here. And what you're doing is you're using the table in reverse. So you have your 0.45 here, right? So you're looking inside here and you're looking for the 0.45, right? Okay, so in this particular case, right, your 0.45, it isn't exactly in the table, right? But what you're seeing is that okay, so it is essentially in the middle over here, right? The 0.45 is in the middle over here, because if you consider 0.450, right, you have 22 to get to this side, and then you have 17 to get to this side, right? So not quite exactly in the middle. But if we're going to use an approximation over here, what we want to do is we want to take the value between, okay, so 0.1 and between the 0.02 and the 0.03, right? So between the 0.02 and the 0.03 would be 0.025. So what's inside over here would be the probability that would give me the 0.45, which would be inside there would be the 0.125, right? Which is this here, right? The 0.125. Okay, so I'm looking at this statement over here, just using the tables, right, using the right tail. So that minus z over here turns out to be 0.125 from using the table. Okay. If you're not happy with the reasoning over here and that you pick in this value in the middle, right, if you want it to be more careful, right, you could use the interpolation, right? So the interpolation, an example of how to use the interpolation is over here, right? Page 148 of the course notes. Anyway, alright, so we get to this point where this minus z over here is now 0.125, right? Okay, so your minus z is 0.125, and that allows me to figure out what the z is, right? The z is negative minus 1.25, and remember, we're expecting the z to be negative, right? So we get the small z is this, and but we still need to figure out what the x is, right? That's the point of the problem. We need to figure out what the small x is. Right? We want to figure out what the small x is over here, right? Okay, but the z over here, small z, was equal to x minus 40 on 6. Okay. So now that I know the small z is minus 0.125, I just simply substitute it in over here. So using that small z is x minus 40 on 60. Put in what the small z is and just solve for the x, and you get this over here, right? So the small x is 39.25, and you want to notice, so that's your answer, and you want to notice that it is less than the 40, right? The 39.25 is less than the 40. Okay. Okay. All right. So to finish this lecture, let's just do this application over here, right? These examples you can take a look, right? I will do this example over here. There are others you can read through. Okay, so you have electrical firm making light bulbs, right? And the lifetime of the bulb is normally distributed. Right, with a mean of 800 and a standard deviation of 40, right? Okay, so if you're doing these problems, first thing is you want to figure out what your random variable is, what you're interested in, right? And give it a name, right? Okay, so what we want probability that the bulb burns, right? Between this range, right? So probability that the bulb burns, right, is, well, the bulb is burned provided it didn't die as yet, right? So what you're looking for is you want the probability that the lifetime is between this value and this value, right? Okay, so you let x, big X, your random variable, be equal to the lifetime of a bulb, right? And you're given that the big X is normally distributed with mean 800, standard deviation 40, right? And what you want is the probability that the lifetime is between 778 and 834. Okay. Now this is with an x over here that is normally distributed. This is not a standard normal, right? Okay. So how you work this out is you convert to standard normal distribution. Okay, so we saw that before. I was talking about that for this lecture. But just to remind you, how you convert is you use this formula over here, right? So this is the conversion, right? And the conversion is using this substitution, right? Okay, so the 778 will, what you're going to have is 778 minus the mean 800 divided by the standard deviation, right? So minus the mean divided by the standard deviation. Likewise over here, so what you get is probability that the big Z is lying between these two Z values. Okay. Right, and we saw how to do this already, right? I explained this using the red areas and the blue areas, but let me just remind you. Right. Okay, so what we want is probability that the big Z line between 0.85 and 0.55, right? You could probably freeze the video and take a look at this over here, right? But so this red area over here, right? How you get it is you're going to take the probability from 0.85 going back, which is this, right? And then you're subtracting off this blue area over here, which is probability from 0.55 minus 0.55 going back, right? So the blue is coming back here, right? Okay, so I get that the probability for my two-sided is the difference of probabilities for two one-sided over here. And these are basically, well, from what you want to do is you want to use these, and from using these, you're going to get something that you can get from the table, right? So you still need to do a little bit of manipulation over here, right? Okay, so ZM less than 0.85, and again we did this already, but I will just remind you. Okay, so if you have, so what we're looking at is values, random variable less than a value, right? And the formula to use depends on this value over here, whether it's positive or negative, right? So if it's positive or equal to 0, you can use this, right? This is coming from using complements. So in this case, this is positive over here, the 0.85. So what you're going to do is this probability z less than 0.85 is 1 minus probability z bigger than 0.85, which is this. Okay, and again we're going to be using this formula, but in this case for this one the small z is negative. So if small z is negative, you use this, and what you're doing over here, going from here to here, is using symmetry now, right? So this here is z, and now that is equal to probability big Z bigger than the negative of this, which is positive, so you get there, right? And then from these you're just going to get these from the table, right? So let's pull it from the table, just as by now you should know how to do this, right? Okay, so what's the first one? The first one is 0.85, right? Okay, so your 0.85, you come down here, 0.8, and then 0.05, so 0.85 would be this 0.1977. Okay, and the next one is 0.55, right? So you add 0.5 and then you add a 0.05 to get this 0.2912. Right? Okay, so you calculate these probabilities over here and then you work out your answer. So your answer is this 0.5111. Okay, so this essentially is now the end of the first half of the course, right? The first half of the course is probability, right? Okay, this section over here, this 6.4, so what we just did was, well, 6.4, right? This is mislabeled, right? Anyway, this section over here, normal approximation to the binomial, this is dropped from the course, okay? Right, so this is gone from the course, and this would have been the last section on probability. And now what we will do next time is you're going to do random sampling, and this now random sampling is the statistics part of your course. Okay, all right. Okay, so next thing I should mention is your midterm is going to be based on probability component of the course. So your midterm is going to be based on the material that we covered. So this section over here, your applications of the normal distribution, and everything going back.